Chapter 4.3, Riemann sums and definite integrals. Day 1, definite integrals. Now we've been looking at the area underneath a curve, using infinite rectangles of equal width to find the area under a curve. Well, several hundred years ago, a guy named Riemann came along and said, why do they have to be equal area? Why do they have to be equal width? Why can't we just make the rectangles however wide? That's basically what a Riemann sum is. You're adding up the rectangles. Still rectangles, just you don't have to have the same width along the way the whole time. And you're still going to have an infinite number of rectangles. What's new is the symbolism we're going to be using today. The symbolism is going to look a lot like an antiderivative, except it's going to have these values on here, a and b. So what this means is we're going to be finding the value under our function. F of x is the function. We're going to be finding the area under the function. And we're going to be doing it from the left side to the right side. That's called a definite integral. In the past, the antiderivative we've been using have been indefinite integrals because they did not have that a and b on there. The a and b limits it. It's definite because there's a left side and a right side. It's a definite integral. The integrals we've had before did not have a left or a right. Right? So let's kind of look at what this means. All right. First off, continuity implies integratability. So if a function is continuous, you can find the area underneath it. Right? That makes a lot of sense. Right? If the line doesn't have any gaps, you can find the area underneath it. That is, the antiderivative from a to b with respect to x exists. All right, so what does this mean? All right, more of what I've said. All right, good, an actual example. Let's evaluate the definite integral antiderivative of 2x with respect to x from negative 2 to 1. All right, what this means is we want the area underneath the curve y equals 2x. And let me draw that out. Area under the curve y equals 2x. We all know what it kind of looks like. From negative 2 to 1. From negative 2 to 1. So we're looking for this area underneath this line to the x-axis. Now here, this part, because it's not actually underneath the line, to denote something that's not actually underneath the line, but between the curve and the x-axis when it's above the line, because it's opposite, we'll go negative. So we're looking for this area underneath the line to the x-axis. Because this portion is not under the line, we're going to go negative that. All right? So we got to find the area of these two regions. And those two regions are both shaped like triangles. So we need to find the area of this triangle, which will be a negative, because it's not underneath the line. It's underneath the x-axis instead. So anytime an area is underneath the x-axis, we're going to say it's negative. So we're going to find the area of that triangle be 1/2 the base times the height. Well, the base is 2. And the height, since it goes down, will be negative. And at negative 2, it's negative 4. So that portion, this triangle right here, this triangle right there, that area will be negative 4. And then we'll need to find this triangle right here. Again, 1/2 the base times the height. The base in this time is 1 because we go to 0, 1. So it's 1/2 of 1. The height is 2 times 1 is 2. So that will be an area of 1. And so when we add those two regions together, we get our overall area to be -3. So the antiderivative from -2 to 1 of 2x with respect to x is -3. All right, let's do it a couple more times. What is the area underneath 4 from 1 to 3? All right, so let's sketch this out. We got a rectangle. The height is 4. 1, 2, 3, 4. And it goes from 1 to 3. Well, area of a rectangle is base times height. Here the base is 2. The height is 4. Oh, that area is 8. So the antiderivative from 1 to 3 of 4 is 8. If we look at B, all right, we got to find the area under the curve x plus 2 from 0 to 3. Well, x plus 2 starts here, goes up by 1 from 0 to 3. All right, that's the area we're looking for. And it looks to me kind of like a trapezoid. Right? Kind of a trapezoid turned sideways. Here's our two bases, and here's our height. Well, the area of a trapezoid is 1/2 the height times the sum of the bases. All right, in this case, our height is 3. So it'll be 1/2 of 3. And the sum of the bases, this base is 2. And this base is 5. So we got 1/2 of 3 times 2 plus 5. This is 7 times 3 is 21/2. So that definite integral is 21/2. Letter C. If you remember anything about the graph of 4 minus x squared, this isn't a tough problem. If you don't, you probably should review it. All right, so we'll graph it. As you do this, you're going to want to zoom to a decimal setting. All right, so y equals the square root of 4 minus x squared. What shape does that make? Well, looks to me like a semicircle. All right, so to find the area right here underneath this graph, to find the area underneath that graph, what shape is that? It's a semicircle. Well, we're going to need to use the area of a circle then. Area of a circle is pi r squared, but since it's a semicircle, we'll cut it in half. And what is the radius here? Well, from the middle to the edge, it's 2. So this will be pi times 2 squared, which is 4 over 2, which we can simplify to 2 pi. And if you want to go to 6.28, that's fine. All right, so review. A definite integral is another way to express the area underneath a circle. The antiderivative of f of x with respect to x between two values, say a and b, what that means is we're looking for the value underneath the function, or the area underneath the function, from a to b. And we're accumulating these rectangles, just like we accumulated before, from left to right. We're accumulating these rectangles from a to b. That's our antiderivative, our definite integral.